My name is Jakob Foerster, and today I'll talk to you about self-play and zero-shot human AI coordination in Hanabi. And I've put these terms, human AI and Hanabi, into brackets because really the zero-shot setting applies both when you're interacting with humans in a zero-shot setting and when you're interacting with a new AI partner that you haven't met before. And also, while I'm presenting these ideas in the card game Hanabi, because it's a fantastic testbed where these ideas can be directly tested and applied, the ideas and methods and challenges are fairly general to partially observable, fully cooperative systems. And by the way, I should mention, I'm a research scientist at Facebook AI Research, and I'm due to start as an assistant professor at the University of Toronto Vector Institute this fall. Great. So the roadmap for this talk is as follows. First of all, we'll introduce these challenges of theory of mind, reasoning over the beliefs of others, and then the testbed, the Hanabi challenge. In the first part, we'll talk about self-play, and in particular, we'll present the Bayesian action decoder that addresses some of the idiosyncratic challenges that are associated with partially observable, fully cooperative systems when we use learning algorithms. And then in the second part, we'll get to what I think is an even more underexplored area, which is zero-shot coordination. How do we learn methods that are suitable for coordinating with a stranger that's trying to coordinate with us? And here we'll present our initial step in this direction, OtherPlay, which is an algorithm that lets you learn these kind of methods. And note here, we will put you into the shoes of a learning algorithm where you have to decide what strategy to play when you are coordinating with a stranger. Without further ado, let's talk about theory of mind. Imagine that you're cycling down the road and suddenly you see a person next to a bus stop raise their hand. Well, immediately you can reason over why that would be, and you suddenly realize that there must be a bus behind you. And that's because the person raising their hand is probably a signal for the bus to stop. That means there's a bus behind you. And this ability of humans to interpret the actions of others when observing them, and to also act in a way that's informative when being observed by others, is commonly summarized as theory of mind. And it's absolutely crucial whenever humans are interacting amongst each other. Doesn't matter if they're communicating or otherwise coordinating, but also when we want to coordinate with humans as AI systems, right? And this theory of mind is in particular relevant in partially observable, fully cooperative settings, which is what we'll focus on in this talk. And clearly, I've shown this bicycle example. This is hugely relevant in traffic. If you want to build an autonomous car, you have to be able to model other participants. As recently Waymo has noticed, that in these highly interactive settings, such as merging, you could extend this with, say, intersections or other social settings, you have to simulate other human traffic participants, which they say is a rich area of ongoing research. Now, let's be clear. If you don't have this ability of interpreting the actions of others, reasoning over beliefs, points of view, and intents, and trying to understand and model other traffic participants, that's like trying to understand dancers when you can't hear the music. In other words, it's an entirely impossible task. We have to start thinking about this very, very seriously if we're serious about predicting or understanding human behavior. Now, we might think that given how important all of this is, it's probably been studied a lot in some of the favorite games that we look at in AI research, because at the end of the day, games have been this testbed for trying out ideas in AI. But perhaps surprisingly, that is not the case. It doesn't matter whether you look at shogi, chess, Go, backgammon. All of these are two-player zero-sum games. Now, for diversity, we do have a few games that aren't fully observable two-player sum, that are partially observable two-player zero-sum. So that's Dota, that's StarCraft 2, that's two-player poker. And then, in fairness, some work has been done on n-player poker. But those are all very, very different from fully cooperative partially observable systems. So there's this huge gaping hole, big question mark. Why aren't we studying these settings? Because I don't really want AI systems that can beat me at poker, beat me at tennis. I would like to have AI systems that can cooperate with me, coordinate with me, and communicate with me. And those crucial skills will require theory of mind. So maybe this is enough. Maybe two-player zero-sum is sufficient. All the interesting questions can be asked and answered in this setting, in which case this big gap in the top right corner isn't so bad. However, unfortunately, that's not the case. For a start, even self-play in fully cooperative, partially observable settings has unique challenges to do with the interpretation of beliefs and actions of others, which we'll talk about in part 2. But perhaps more surprisingly, two-player zero-sum is really a very bizarre and special setting where all the Nash are created equal, or technically speaking, interchangeable. And what this means is that any variation of self-play that guarantees no regret during self-play and therefore finds a Nash equilibrium means that you cannot lose when you match with a stranger at test time. So in some sense, self-play is all it takes. Good self-play that finds a Nash equilibrium is guaranteeing you not to lose, not to do poorly at test time. In contrast, in fully cooperative partially observable settings, even a perfect self-play policy can be arbitrarily bad when paired with a stranger that's playing a good policy, right? So what this means is that we need fundamentally new algorithms, formalisms, and solution schemes for the fully cooperative case. And in particular, when we think about coordination settings that are zero-shot or ad hoc, including humans, we don't even know where to start. And we'll make a little bit of progress here, though, in this talk. And this is being done in part 2 of the talk. We will do all of this using a framework called reinforcement learning, where we assume that there's an environment on the right-hand side and there's an agent on the left-hand side. The agent obtains observations and rewards from the environment and takes actions U. Next, based on the Markov state S and the action U, the environment undergoes a state transition where new state S prime is sampled from a distribution over states P of S prime given S comma U. Note, though, that while the state is dynamic and updating, the environment itself is assumed to be static, i.e. the transition probabilities and the reward function are static. And this means that the agent can interact with this environment many, many times or to learn an optimal policy. An optimal policy is one that maximizes the total expected return per episode, which is the sum of the rewards discounted by gamma, the discount factor. Now, I want to emphasize this again. In single agent reinforcement learning, it doesn't matter why a given action U was taken. I don't care about which policy generated this U in order to understand what's going to happen next. All I need to know is the Markov state S and the action U. And that means exploration over actions is perfectly appropriate in order to learn a good policy. Because we care about settings that have complex observation spaces and high-dimensional action spaces, we will use deep reinforcement learning, where the agent is parameterized as a deep neural network that processes the observation and then produces distributions over actions or expected Q values. And we'll typically use theta to indicate the weights of the agent. Because I'm interested in multi-agent learning and theories of mind and beliefs, clearly having a single agent isn't enough. Instead, we're going to have another agent, the blue agent, and the green agent. And note here, they all obtain their own observations, their own rewards in generality, and take their own actions U. What's important, though, is that what happens in the environment, the next state S prime, depends on the joint actions of all of the agents, the red, the green, and the blue. And this means that this is a fundamentally challenging problem. We could try to ignore the presence of other agents, i.e. there's a naive learner here, the red agent, that just pretends that the environment is all there is and folds the other agents into the environment. The challenge is now that because other agents are learning, this environment becomes non-stationary from the perspective of the red learning agent. And that's obviously a huge challenge. Instead, we could try to model the presence of other agents by having a belief over their policies and their changing policies. But note that if each of the agents has a belief over other agents, their belief clearly changes how they'll act in the future. And therefore, I should probably have a belief over the belief of other agents. And you can see this will lead to an immediate explosion in complexity, which is quite typical when we have agents reasoning over other agents in a complex environment. And yet, humans somehow manage to cut through these explosions, and we will have a few methods that do something similar in these multi-agent settings. Now let's fill in that gap. We believe that this huge gaping hole in the top right quadrant can be partially addressed by Hanabi. Hanabi is a partially observable, fully cooperative game where all the players are acting as a team. And the twist in Hanabi is that you cannot see your own cards. Therefore, communication through actions, interpreting the actions of others, is absolutely crucial in order to succeed at Hanabi. A brief explainer. The first key component of Hanabi are the fireworks. These are stacks of cards, one for each color, that you have to build. You have to start with a 1 and end with a 5. It's much like a cooperative form of solitaire, or collective counting, as Mike Boning likes to call it. The twist is that you cannot see your own hand, so therefore you don't know what cards are playable and what cards aren't playable in a given situation. To make up for this, the other players can see your hands, and they can also provide hints. They can point out sets. So for example, they could say the first and fifth cards are 2s, or they could say the second card is red, but note, they can only point out sets. So for example, I can't say your third card is white. I would have to say the third and the fifth card are white. Now those hints are costly. So clearly, if I had to point out every single feature, I would run out of all the hint tokens that are in the game. So instead, we have to interpret the reason why a certain hint was given. Imagine you're in this game situation, and suddenly you tell your friend, your first card is yellow. The friend might ask himself, well, why would you tell me this? Well, the goal of this game is to play cards. Maybe my first card is playable, and they would play this card. And they would do this by reasoning over your intent for telling them what you just told them. So we believe that this is one of the great new challenges at the frontier of AI research, and we published a paper on this with code and so on. You can find this all online. So let's talk about self-play. What are we doing in self-play? In self-play, we are training a team of agents to maximize the expected return when they're being tested as the same team. So here pi star is just the argmax when we're pairing pi1 with pi2, and that's it. And we're doing the same during the training session. It's the Brazilian team playing together as we do at test time. And that seems like a very reasonable thing to do if you want to have a team of robots that gets deployed together and never has to collaborate with anyone else in the world that isn't part of the same team of robots. We address this setting partially by the Bayesian action decoder, bad acronym here, for deep multi-agent reinforcement learning, which was published last year at ICML. And it was great work with my collaborators at DeepMind and Oxford. So let's talk a bit about Bayesian reasoning and communication. So imagine that you have Bob. Bob's holding his hand this away from himself, but Bob has a belief of what hand he might be holding. So this is P of HB, the hand of Bob. And then Alice joins the game, the teammate. Alice takes a look at Bob's hand and then says, hey, the action of Alice, I will discard my fifth card. So what should Bob do? Well, Bob should not update his belief because he just obtained the information. Alice looked at his card and then decided to do something. That's fundamentally a Bayesian problem. And you can look at Bayes' rule here. So this is P of X given Y, right? So this is now the belief of Bob over his hand, P of hand given the action of Alice, which is nothing but the Bayesian posterior. Note, however, because we're doing centralized training, the probability of the action given the hand is nothing but the policy of Alice in a simplified form here. And what you can see here is that the posterior belief of Bob over his hand doesn't just depend on the action of Alice and the previous belief, it also depends on the entire policy, i.e. in what other states would Alice have taken this action. So what does this mean? It means we have to fundamentally rethink exploration and credit assignment, because no longer is the next state as prime a function just of the previous Markov state and the action that was taken. What happened? It now suddenly depends on the policy of Alice, which is why it happened, right? So this means that the future of what happens in the game next to Markov state isn't just a function of what happened, but also of why it happened. And this has two drastic consequences. For a start, we have to stop exploring over actions. We have to explore over policies rather than actions. But also we have to treat the belief as part of the state. Because clearly exploring over a policy is only meaningful if I then form the associated correct belief, this Bayesian posterior, with that policy. We have to get the correct belief, B prime, conditioned on the previous policy that was explored and the previous action that was taken. And if you put those two things together, then it pretty logically follows you have to have a public belief to avoid the circular reasoning. And that's exactly what the Bayesian action decoder does. So what we do in this Bayesian action decoder is we sample a mapping from private observations to actions, which is conditioned, which is sampled from distribution that conditions on the public state. As I said, it has to include the public belief because now we're exploring in a state that is over partial policies, and we have to form the corresponding belief whenever we try out a policy. And FPUB here is the other public features. The acting agent then evaluates this partial policy for the private observation. So that's, you can think of like the message of a sender. I want to send the deterministic message here. And this action UAT from the active agent is then observed by all players and also sent to the environment where it's executed to obtain the next state as prime. This is the environment state, not the Markov state for a problem. And because we have the policy that generated the action, we know the previous belief, we can now form a public posterior. Note, because only public information was used on the right-hand side, because the way that we generated this partial policy is based on public information, the updated belief BT plus 1 is also still public. And that means all agents can independently agree on the exact same belief. What this means is that we can now represent this partially observable multi-agent problem as being a Markov system over a public belief MVP. So here, the Markov state of this new system is the public belief over private features, the public features, and the policy now produces an entire partial policy as an action. It's no longer enough to say, this is the action I'm taking. I have to say, this is the action that the active agent would take in every possible private state. And that's because the new state, B prime, conditions not just on the environment action U, but on what would have happened in every possible state because it's a Bayesian update. It depends on the counterfactual actions. So we can now in principle solve this with any deep RL method of your choice that's appropriate for feed-forward methods. And that's indeed what we did with a lot of adaptations, because this is a very, very hard problem due to the extremely large states and action spaces here in this representation. But if you do all of this, you do, for the first time obtain a new state of the art. So in Hanabi, you can get 25 points, which is 5 stacks of color of 5 points each. And no one had obtained 20, you can't obtain 25 points in general on average because they're unwinnable decks and we don't actually know the upper bound, but there have been hand-coded heuristics that were based on sort of human expertise in the game that obtained reasonable scores like 23.5. Previous learning methods were awful. They got around 14 points, I believe, in this game. But the Bayesian actually could have got 24.2 points in expectation. And it also obtained a win rate that beats all the bots that we knew about at the time. We didn't actually know about Fireflower when we did this work. We discovered later on that we did beat Fireflower, but that was, you know, just a lucky coincidence because we do have a very strong method. Around 58% win rate, which is when you get 25 points in a deck. It doesn't just get the highest final score; it also learns fast. So here you can see the red curves. That's the Bayesian action decoder, and the blue curve is our baseline method. And you can see this distribution of scores. It really gets very high points all the time. What's interesting here is we didn't tell this bot anything about any conventions, and yet it learned to do interesting gameplay where it would use red or yellow, these hints, red or yellow cards, to indicate that the newest card should be played. And it would use white and blue to say that the last card should be discarded. We gave this bot a few printouts to David Wood, the creator of Fireflower, and he said that this bot is very, very strong in the early game, and the convention set is far more efficient than natural human convention set. It's really quite beautiful. So there has been more work ever since on this. In particular, we've published 2 papers. One of them is a simplified action decoder for deep multi-agent reinforcement learning that was published at ICML 2020. And then we further improved on these methods using search, which was a paper at AAAI. And we've now raised the state of the art, in particular for 5 players, from like 17 points roughly from the challenge paper using large-scale active critic methods to almost 24 points. And note, these things can be trained on a GPU in a few days on a single GPU. They're extremely resource efficient at training time. And then obviously like the search process will take a bit of time, but even that can be done on a single GPU. But let's take a moment here. So these convention sets are great in self-play, but is that really what we are about? Because they're very different from the natural human convention sets. So let's switch gears completely. Let me convince you why I think we're asking the wrong questions and what the questions are that we should be asking. This is formalized as zero-shot coordination. So imagine that instead of training the team of agents to do well with itself at test time, we're now training 2 different teams of agents, the Brazilian team and the Argentinian team. And the challenge is that without ever being trained together, they should be able to do well when tested in crossplay, i.e. when being matched half and half. The twist here is to make this at all feasible, the coaches can agree on a training strategy before training starts. What should the strategy be? And this is a very surprisingly hard problem because it sounds like we have an objective, crossplay, why can't we just optimize it? Well, the answer is you can't because you're not allowed to evaluate this objective during training. By definition, the crossplay, the zero-shot interaction, is the first time that these 2 halves meet. And therefore, if you were to use the crossplay score during training, you would violate the spirit of zero-shot coordination. And indeed, it's very easy to tell after training that you failed because you get a low score, but there's no known scalable algorithm that exists to solve this problem in general. And we'll show you a step in this direction in this talk. This was published as Other Play for Zero-Shot Coordination with my fantastic collaborators at FEA, and it's a paper at ICML 2020. Obviously, this paper is on arXiv, you can find it there. The formal problem definition is as follows. Suppose that multiple independent AI designers construct agents that have to interact in various but ex ante unknown deck DPs, decentralized partial observable decision processes, without being able to coordinate beforehand. What learning rules should these designers agree on? And this problem is hard even in the simplest cases. So now let's put you into the shoes of an agent. we're posing you a challenge and you have to decide what you should do. The task description is as follows. You need to cooperate with a random stranger by choosing one of the 10 levers shown on the left-hand side. If the two of you pick the same lever, both of you get the reward shown next to the lever in the image. So for example, this lever gives you 1 point, and this lever gives you 1 point, and this lever, I'm going to call it out, gives you 0.9 points. Otherwise, the reward is 0. So if you pick this lever and the stranger picks that lever, you get 0 points. You have a single attempt with a stranger. And the task description, so the goal, exactly what you're seeing here, is common knowledge. The stranger will be presented with exactly the same information. So this is you, this is the random stranger, looking at the same problem, and you pick a lever. Let's play through a few scenarios. What do you do? So first of all, what we could do is, we could model ourselves and imagine that we have an imaginary twin on the other side of the world who goes through the same kind of reasoning process. First, obvious idea is, let me pick an arbitrary 1.0 lever. So let me play this through in my head with my imaginary twin. I really like that lever, but my imaginary twin, by the same reasoning process, picks a different arbitrary 1.0 lever. So clearly this is a coordination failure. Well, since all the 1.0 levers are ruled out, we could now try and pick the 0.9 lever. And again, my imaginary twin has gone through exactly the same reasoning process, so it's also arrived at that conclusion. And suddenly we get coordination success. This is an extremely simple game, and yet our machine learning software algorithms simply can't solve this. Our key idea for solving this is around symmetries. So in particular, in this DEC-POM-DP, assume that there's something called phi, a symmetry. And it's only a symmetry, it's if and only if a symmetry when it leaves the structure of the DEC-POM-DP unchanged. What we mean by this is, phi can act on states S, S prime, actions A, and observations O. And essentially, as long as the topology of the DEC-POM-DP, what states and what actions lead to what next states, what rewards, and what observations, is entirely unchanged when we apply phi, then this is a symmetry of the DEC-POM-DP. And because we can apply it to states, actions, and observations, we can also apply it to policies by simply having the policy act on the permuted, on the changed DEC-POM-DP. Now this is quite abstract, so let me make it a little bit more explicit. So you have a robot in a world that is 2D, X and Y axis, and this robot has to go to a goal in the middle of the world. Let's also assume the world is symmetric around the X and the Y axis. And clearly, if I take this robot here and I invert the Y axis to the bottom right corner, then going down in the top right, i.e. taking the left action, is equivalent to going upwards in the bottom right, because I'm getting closer to the goal. And that means I can't just invert the axes, I have to also flip the corresponding action space. So I have to exchange the green and the yellow action here to then keep the structure of the DEC-POM, this process unchanged. And the same is true for the bottom left, where I have to switch all of the actions, red and blue, green, yellow, and for the top left, right? So these are symmetries. Symmetries are things that leave the structure, the graph structure, unchanged. Obviously, they're hard to calculate in general because that's a graph isomorphism, and that's an NPR problem. But if we know those symmetries, then we can do the following. We can go from self-play to what we call other play. And the idea is very, very simple. In self-play, I could agree exactly on the two policies of myself and my teammate, pi 1 and pi 2. I could optimize both sides to do well together and only do well together. I don't care about anything else. In other play, however, I have a bigger requirement. I'm requiring that if I'm breaking symmetries in one way or another, then I have to be robust to my imaginary twin, breaking the symmetries in an arbitrarily different way. And that's done by having this permutation phi that I sum from all permutations at every time step act not on both of us, because that would leave everything unchanged, but only act on their world. So this is exactly specifying my partner and my imaginary twin only up to the set of equivalence classes. So remember when I said, oh, what if my arbitrary twin picks a different 1.0 lever? That's exactly that. Phi says they're all equivalent, therefore I have to be robust to symmetries being broken in a different way from how I did it in this specific run. And what this does, it calculates an expected return, an other play objective, which is the expected return over the entire symmetry class. We're matching all the policies in a symmetry class randomly with each other. We calculate the expected return. And clearly, if you can do this, and if both sides do this, then we would end up with a policy that's robust to doing the arbitrary handshake that self-play does in a different way. And we note here, other play, when you know the symmetries, is the best possible meta-equilibrium. And you can actually implement other play on top of any deep algorithms of your choice, because you simply can permute the action state, action space, observation space, and the reward function. So let's look at what the symmetries are in Hanabi. In Hanabi, it turns out the colors are all equivalent. There's no labels in the graph as per the definition of the problem. So yellow, red, white, blue, green all look exactly the same from the graph structure, from the functionality. And that means each phi is a permutation of these colors. So what this means is, we're looking at one example here where we switch yellow and white. My view of the world looks like this, where there's a yellow card, a yellow one, a white 5, and red 1, and my hand has a yellow 2, or your hand has a yellow 2 at the first one, then I can hint to you by saying your first card is yellow. In contrast, for my teammate that lives in this permuted world, phi, the fireworks are switched out, they're reshuffled, because now there's a yellow 5 and a white 1. Also, the hand is reshuffled, so now the 2 is white and the 3 is yellow. But the semantics aren't changed, because now if I hint your first card is white, then that still is hinting towards the playable 2 in the first position, because we permuted the action space and we permute the observations and the fireworks. And crucially, imagine that now, if you're doing Hanabi, you have an agreement where you say the first card, red means play the first card. Because the world is reshuffled for one of you, you don't know that your red card possibly is my yellow, and so on and so forth. Right? So you have to be robust to these symmetries, arbitrary choices being made in a different way. What does this do in the simple matrix game? In a simple matrix game, at training time, it looks like self-play is winning, because self-play gets 1.0 points, because these self-play agents can arbitrarily coordinate on one of the 1.0 levers. In contrast, other play gets 0.9. But now let's look at testing. At test time, other play gets 0.9 points in expectation when paired with an independent seed. And self-play completely fails to coordinate and gets around 0.11 points in expectation. Now, this also works in Hanabi. So in Hanabi, we're looking at self-play on the left column and cross-play, where you match independent seeds with each other on the right-hand side. And indeed, if you're looking at the standard SAT agent, it gets around 24 points in self-play. But in cross-play, when you're matching independent seeds, it gets 2.5 points. Right? This is drastic failure to coordinate. And obviously, you can't expect to coordinate with a human if you can't even coordinate with independent runs of yourself. But this is what most of us are doing. We're doing self-play methods, expecting that we can learn policies that can coordinate, which is ludicrous, right? We need fundamentally new ideas here. The same holds up if you add an auxiliary task, which brings up all the self-play scores and also helps with cross-play in general. But even then, you get another boost from adding other play. And you can see this in these matrices. So these idiosyncratic color usages here for the SAT agent, they disappear when you use other play. And then if you add the auxiliary task, you get these very smooth looking matrices where actually the hints are being used in a semantically meaningful way. So now suddenly when the agent hints the first card is red, it does actually mean the first card is red. It might also imply other things, like it's pointing to the card or means something else about the card, but it is about that card. It's no longer arbitrary. It's no longer arbitrary handshakes, which are so permanent in self-play. And you can see in the crossplay matrices, so in particular, the SAT agent really only works with the exact same seed of itself, or the off-diagonal scores are poor. And then if you do other play and the auxiliary task, you get this wonderfully filled in matrix corresponding to the high score, where all the seeds are roughly compatible. But none of these seeds are perfect. So we still don't have a method that gets perfect score at test time. You know, only when train equals test are you not doing any idiosyncratic handshake during training time, and we don't have anything like this right now. What's perhaps more impressive is that being better at coordinating with a different seed of yourself directly translates into doing better with humans at test time. And that's shown here. On the y-axis, we have the other play bot for a number of different seeds. And on the x-axis is the previous state-of-the-art self-play bot, the SAT bot. And what you can see is that for almost all of the seeds, the other play bot drastically exceeds the performance when matched with humans in a zero-shot setting. These humans were not told anything about this bot, apart from the fact that it's trained on Hanabi and knows how to play the game. And obviously the expectation is much, much higher than on the self-play bot, around 16 versus, I forget, 6. Clearly, we're not done with this. In particular, there are huge open questions along this long journey. And I think we're just taking the very first steps in understanding how we can make progress in coordination issues, forgetting about self-play. For example, what happens when we don't know the symmetries, right? Other play currently takes the symmetries as an input, but humans manage to discover reasonable policies without being provided the symmetries. This also begs the question, how can we learn to adapt on the fly, right? Humans excel at interpreting intent. I see a few actions and understand what this the other player is trying to do. So the humans are really, really good at adapting to a broad range of different policies. What's the magic here? I think what this all comes down to is we have to stop thinking about solving our problems by providing one self-based solution. That's just not appropriate, right? RL currently learns about the problem when finding a solution, but those have to be two different steps. We have to first be able to understand the landscape of all possible solutions, and then later on decide which ones of these we should play at test time when we're trying to coordinate. And what this asks for is the question, can we learn other play and similar algorithms? Right? I think we're again like really early on the journey, and we do want to make that journey as easy as possible for everyone who's excited about this. So we've open sourced the Hanabi learning environment, we've open sourced the code for Hanabi search, we've open sourced the code for the simplified action decoder, including pre-trained state-of-the-art RL agents, and we will open source the code for other play in the future. So with this, I encourage you to join me on this journey. Let's really start thinking about coordination deeply in these fully cooperative partially observable settings, because it is absolutely crucial and it's entirely underexplored in the scientific community. With that, I'd like to thank you all for listening, and then hopefully there will be some questions online later. Be safe. Bye.